Alright, so today I just wanted to clarify a few more things about some waves. We kind of talked about what they are, what they look like, maybe the main parts of a wave, which I've written some of those down here. I haven't written amplitude, as you can see. But some of the things I wanted to talk about. One thing has a lot to do with geometry. Okay, so before I get too deep into too much, the one thing I haven't written down here, I've written down up here, which is amplitude. If you talk about the amplitude of a wave, remember that's basically the height of a wave, right? So if you're talking about this, and notice that this time I didn't draw that central line on this thing, right? So you'd have to find your midpoint of the wave, and let's say it's about there. The amplitude of the wave would be the height up from that, or, remember, down from that. So it could be from the midpoint down to the bottom of the trough, or from the midpoint up to the height, the crest of the wave, right? That's your amplitude. Now that's all very interesting and everything else. I'm sure you're super excited about that. But one thing I wanted to show you is this. Let's go ahead and start taking a look at this, some actual amplitudes. And hopefully you'll be able to see this here. Okay, so you can kind of see the wave now. See, it's kind of going back and forth. It's making a standing wave. Well, you can probably guess what the amplitude is. You can kind of see where the midpoint is. It's right about, sorry, not enough hands here. It's right about there where the top of my pinky is the midpoint. So if you measure from there up, you'll be able to find the amplitude of that wave, right? Or if you measure down from that point, you'll be able to find, to the trough, the amplitude of the wave. So that's all well and good. But what happens if I take this device and I start to tilt it at some kind of an angle? Now that's still the exact same wave, is it not? Well, look at it now. Is the apparent amplitude still the same? It's not. So what happened? Well, what I do with this device is at first I showed you full on what the wave would look like, and then I started to tilt it. So all of a sudden, the thing that looked large before, as you tilt it, looks smaller and smaller and smaller. So it's a weird thing, and you see this in geology too. I have a lot of background in that one, right? What you notice is that when you start looking at things, if you look at them exactly end on, that is the maximum size they get to be, right? So the maximum amplitude is the one where you're actually seeing it perfectly perpendicular to it. If you start to look at some kind of a weird angle, it looks smaller and smaller and smaller. And if it goes the other direction, if it comes towards you again, it still looks smaller and smaller and smaller overall. So you can get an apparent amplitude, which is when you are rotated with respect to this object, right? If this is your wave going up and down like this, and all of a sudden you start looking at it from different angles, it's going to look to have a different amplitude. So be aware of that. That will come up on questions on the AP. I've seen it a lot of times already. Okay? So apparent amplitude is different from actual amplitude, and it's basically just your viewpoint compared to that of the wave. Okay? So if the wave is going up and down like this, if you tilt your head or stand in a weird way, that wave will appear to shrink until actually you're looking head on at the wave, right? And then it'll look like it has no amplitude. Kind of a weird thing. Okay, so what else do we have? We have some equations I wanted to go over as well. So what kinds of things do we think we're going to need? Well, these are all things that you could be asked to find on a test, okay? The wavelength of the wave itself, and as we remember, right, the wavelength was from any same point on the wave back to that same point. So if we're talking about our scale has meters down here, remember you have to have meters, of course, because you're talking about a wavelength that's in meters. So if I go from a crest, the next crest I find is over here. That right there was my wavelength, okay? If instead this was time, if this was seconds down here, that point to that point would no longer be a wavelength because it wouldn't be meters. If my axis down here was time or seconds, that would all of a sudden be my period. The time it takes to go from one back to the same exact spot, right? From a crest to a crest, or a trough to a trough, or even a midpoint to, and be careful about this, not going back to the same midpoint, but to the next point where you're going back down in the same direction, right? See how this one's headed down this way? You don't want to be going up, you want to be going back down. That's why the midpoints are a little bit squiffy to use, right? So if you go from crest to crest, and your bottom axis here is seconds, you've just found your period of that wave, okay? So frequency is very similar to period, except for it's basically just, well, how in the heck do we get this? Hertz? So I want to use units here, and I want to start deriving some formulas based off of the units alone. It's a very good skill to have. If you look at the units, you'll be able to find out the formula you need, okay? So frequency is 1 over seconds or hertz, same unit, okay? So, if it's 1 over seconds, well, the period is already in seconds, isn't it? So what do you think the formula is for frequency using period? If you have the period, how do you find the frequency? You probably guess it, right? So if this is in seconds, and I want to get to 1 over seconds, what do I have to do? Sorry. I have this in seconds. I want to get to my frequency, which is 1 over seconds. So what do I have to do with my period? I have to go 1 over seconds, and period is in seconds. So frequency is 1 over the period. All right. Conversely, if you flip this equation around, you're going to find that your period is equal to 1 over your frequency. Right? Same thing flipped on its head. Just swap those two terms out. Okay, so that's frequency and period. We got a couple things to work with there. What else have we got? Well, we've still got velocity, don't we? Velocity is in meters per second, isn't it? So let's take a look at these things that we have listed up here, these variables, and let's try and build a formula based on what we know the units should be. So what do we have that's in meters? We have wavelength that's in meters, right? So that's a length of a wave, okay? So we have a wavelength in meters, okay? And what do we have that's in seconds? Well, we have period that's in seconds, don't we? So it could be lambda, our wavelength, over t, our period, right? Is there another way to find this? We need meters on top and seconds on bottom, right? This has seconds on bottom already, doesn't it? So another way to find the velocity of a wave is actually to take lambda, you still need those meters, right? And to multiply it by your frequency. Lambda f, or lambda over t, is your velocity for that wave, okay? So that kind of gets us there. That's our relationship. This is the main one. If you know this one, you're going to be good to go. This is extremely important too, just as long as you know that frequency and period are inverse of each other, okay? So there's some equations for us. What do we got next here? Okay, if you want these back, just to go ahead and rewind the video, I'm going to erase it so I get some more room, okay? All right, so last thing here, I wanted to talk about polarizing filters. We already talked about what happens when you kind of take and turn your head as you're looking at a wave. The amplitude seems to change, right? But what if we do something else here? What if we mess with a wave in a different way? Well, first we kind of need to talk about, I'll go ahead and write those over here, 1 over frequency. It's a terrible F. Let me just go ahead and redraw that fancy F there. This is 1 over period, okay? We'll find that later. Okay, so, couple things first here, before I dive too deeply into it. Magical other land here, right? That's where this Slinky's connected to now. Okay, so now I'm going to make a crest. So here's my crest. I'm going to draw it back. See it there? And watch what happens. You're going to see an expanded side around the crest. And you're going to see a denser side, and that is the crest. So your trough is going to, on a sound wave, or a longitudinal wave, is going to look, your crest is going to look like a compressed area, and your trough is going to look like an expanded area. You see it traveling back and forth. You can kind of see, let me get a little bit more going here. Let me pull it back a little farther. And now you can really see there's kind of a compressed area and an expanded area going back and forth along this thing, okay? So, some might even call it rarefication. All right, so that's one kind of a wave. A sound wave, as I'm speaking with you, we talked about this before too. When I breathe out, right, I'm forcing air out of my lungs, and as I do so, it pushes. But it actually gets hit, right? It runs into the other air molecules that are already there, so it kind of comes back. But those air molecules that are there, action, reaction, right? Newton's laws here, right? So for every action, there's an equal and opposite reaction. When I breathe the air out, it hits something and it stops, and it may even come back at me, right? But the next thing of air gets pushed off until it hits the next little pocket of air, and then it bounces back, and that air keeps on going. So what you end up with is this motion where you have kind of a back and forth, just kind of a vibration in the air. Sorry, let me see if I can get that a little bit better here. Okay, so if I take and you'll see it's just going like this. That's all it's doing, right? That is a longitudinal wave. It's vibrating or oscillating in the same direction it's traveling. What about a transverse wave? A transverse means perpendicular, so it's going to travel this way. It's going to go in the exact same direction it was, but a transverse means it has a perpendicular component to it, and that's probably more what you guys are used to, is seeing a wave that looks like this, right? Seeing something traveling along that has this sort of normal kind of wavelength looking to it, right? So that's a transverse wave, but this is the interesting thing. Transverse waves come in a couple of different types. There's kind of the up and down transverse wave, and there's the back and forth, right? There's the front, back, and side to side, okay? So you could have that exact same wave look like this, which I'm always showing you on camera because it's easier to see, but realize that I can do the exact same thing, but instead of vibrating in the Y direction, I can vibrate in the X direction or the Z direction, right? So I can take this thing and move it back and forth this way, and I get the same sort of motion, right? It's still a transverse wave because the direction it's moving is like this as the wave travels this way. So what those are called is that's different polarities of a transverse wave. So if I have a wave that has an up-down oscillation as it travels this way, if it comes across a filter, which is basically just something that has a bunch of little slits cut into it. In this case, those slits are up and down. That wave will be able to pass right through that filter and keep on going, okay? But what if I get another kind of a wave that's traveling into and out of the board, right? So I'm going to try and draw that. Something like this. It's maybe not the best in the world, right? You can kind of see that it's doing something slightly different, right? And as it comes here, if it gets here, this thing's going out of the board, into the board, out of the board, into the board, out of the board, into the board. And then it comes up across this filter, which is up and down. Well, guess what? It's not going to be able to get through that because each one of these things, if the wave hits here, if this is its crest, it's not going to be able to get through. If it hits here, it's not going to be able to get through. If it hits here, it's not going to be able to get through. Only a tiny little portion of that wave is going to be able to get through at all. So a filter is effectively going to block this in and out wave, but allow the up and down wave to go through. You've seen this before. Here is one example of a filter. And notice what immediately happens when it goes in front of me or in front of anything else. It immediately gets darker, doesn't it? That's because light, unlike sound, is a transverse wave. And so when you put something like this up that has a bunch of these tiny little slits, you can't even see them, they're invisible because they are so small, right? They're so thin. But that's all it is a series of really thin cuts. But you put it in front of something and what happens? It doesn't let one kind of transverse light through, it doesn't let one polarization of it through, but it does let the other through. So it cuts out maybe half the light. All right? So what happens if I get two of these filters? Well, two of these filters should block out everything, shouldn't it? Well, look, they're lined up. They let everything through. They looked exactly like the first filter by itself, pretty much. Right? No difference. But then I take and put them at 90 degrees to each other, and what happens? Nothing gets through. So now it's blocking both kinds. I have two filters, one that's up and down, and one that's side to side, and it's effectively blocking all kinds of light. So, pretty cool, right? Filters will be able to take and remove certain kinds of light, certain kinds of polarity. Where have you seen this before? Anytime you've gone to a 3D movie, you've actually effectively been wearing both of these filters. It's just you've been wearing them, right? If this is 90 degrees, well, let me get that right. There's 90 degrees to each other right there, completely cutting out all light, right? What you've been doing when you go to the movie theater is this, putting one over each eye. And so this eye only sees up and down polarized light, and this one only sees left and right polarized light, and they'll show you two images, each one is polarized, and when you put them over each other, each eye sees something different, and it looks like it pops out at you in 3D. Another place that you've seen filters and polarization is just straight up regular sunglasses. If you have one kind of polarization, it blocks out a good chunk of the light. But what you'll notice is polarized filters on a sunglass can be pretty interesting. If you ever have any of these, go out, check the sun, or so not the sun, don't actually look at the sun ever, right? But go look at the blue sky, okay? If you actually have a filter that's polarized and you look at the sky through these things and you rotate them, you will actually see the color of the sky change from a lighter to a darker blue because the polarization of the light coming from the sky, it is polarized, and it's polarized more in one way than another. So it's kind of interesting. That's it, okay? Long speech, but there you go.